Okay, welcome back to robotics lectures of the course. The next few lectures will be mobile robotics, which include the fundamental part of the vehicle themselves. And then, of course, as you know, we talked about before, mobile robots is like a blind person or a blind object. Doesn't know where it is and where it's going to go. And that are the localization and navigation, which are the next two chapters. So today I'm going to walk you through chapter 4, hopefully complete the whole chapter today, for tonight. And along the way, I'd like you to be cognizant of the fact that there are a lot of information which are assisting the course and the lectures in appendices A through J or K. And those appendices are here. By now you have put your toolbox on your computer. By now hopefully you either reviewed or start learning Simulink. And then the MATLAB objects of the toolbox. If you need to refresh yourself on linear algebra, matrices, matrix inversion, multiplication, etc., you can go to Appendix D. Appendix E will come later on when we talk about localization and navigation. Will come in handy there. Same as these Gaussian random variables. Jacobians are matrices were related to the partial derivative of a nonlinear function with respect to one of its variables. If the function is a scalar, the Jacobian term is a vector. If your function is a vector and you take a partial derivative with another vector, the Jacobian will be a matrix. The most important part of Jacobian matrices is the relationship between the space, joint space and Cartesian space in the manipulator side of the discussion. And I will cover that later on in due time. Kalman filtering is also a good review part for some of you, and undergraduate Kalman filtering it should be over your head. However, don't get intimidated. It's not that difficult to learn. And we use it to estimate the location of a mobile robot. Okay? And it's essentially a Gaussian-based optimum estimation algorithm. And it is named after Professor Rudy Kalman, who created that filter. Homogeneous coordinates, you already seen that in the manipulator section of the course, and graphics, which is the general knowledge. So today you will see that Appendix I comes into the picture in our discussion. So let's now look at, this is a strange, okay, here we go. So mobile robots, going to chapter this is a prelude to chapter 4. Here you see two mobile robots which are historically a long time ago. In 1948, the one on the left, believe it or not, was put together in 1948, which is now in a Smithsonian institution in Washington, D.C., and it's not on display anymore. And then this is Shaky, another robot which was built in 1968, which is now in the Computer Museum in Mountain View, California. SRI stands for Stanford Research Institute. It's a very big research think tank area. These are more relevant and more recent mobile robots. This one is familiar with you for the Mars rover, which was actually went into space in 2004. Exploration rover, Mars, MER, called Mars Exploration Rover, which all of those were commanded and controlled from Jet Propulsion Laboratory in Pasadena. This so-called mobile robot, which is like a sort of ROV, is a recreational vehicle. It's actually a Chevrolet, as you can see here. This is a car that won after the second or third try of what's called DARPA challenge. DARPA, the research wing of the Department of Defense, several years ago, this happened to be in 2007, gave a challenge for the universities and industries, not very large industries, the startup companies, to navigate and basically move an unmanned vehicle from close to Los Angeles along the side of Highway 15 all the way to Las Vegas, a very large distance. In the first or second try, nobody succeeded. I believe this is the third attempt that a group from Carnegie Mellon University in 2007 achieved that, and they received $1 million from DARPA. You know, it was a lot tougher $1 million to earn than the one in Dubai. 2 weeks ago I was there. But nevertheless, both of them were important and are good for challenging our young minds and help them. And as you can see, if it was not for DARPA's challenge, probably Google would not have a driverless car right now, or GM doesn't have one, or Mercedes wouldn't have one, and so forth and so on. So this is the sign of a visionary government agency which can open the path for future industries and future. I was listening recently to a TV scientific show, and a gentleman who was advisor to some of the politicians in Washington mentioned the following. He said that 65% of the title of 65% of the future jobs, at this moment we don't know what they are. Okay, which means technology is moving so fast, and along their way they create new jobs. And it's our challenge and your challenge to learn and keep up with it. You know, I keep telling all my students, including my own, also my own son, to keep retool your skills. Don't just stay too comfortable with one job, with time day and in and day out. So always try to retool yourself and educate yourself. Hopefully this course will give you that kind of capability. The part C is the one which is also familiar with you, the Rombo robotic vacuum cleaner, which was marketed by iRobots, a company which was put together by a bunch of MIT professors and students, and I believe they're currently headquartered in New Hampshire. And then this is an actual working is an actual working port of Brisbane, Australia. I've actually been to Brisbane. It's right by the Indian Ocean, a very beautiful place. Parts of it remind you of Hawaii, actually. And I've also been involved with a similar project in France, at Lille University in northern France. But essentially, you have a whole bunch of mobile platforms on the shore which work together as a group, as a team. And they keep moving material for loading or unloading from a large carrier or to a large carrier. So this also is a mobile platform. One of them is, of course, a mobile robot. If you have a system of those, you're talking about the system of robots. Okay. Now, this is on land. Now they can go to the air and underwater. In the air, you see two up here, a helicopter, which, as you'll see shortly, it has 6 degrees of freedom. And you only have essentially 4 actuators. We'll look at that later. This is an unmanned fixed-wing aircraft, which also has 6 degrees of freedom, namely X, Y, Z, pitch, yaw, and roll. Those are the 6. And then limit less than the number of actuators are less than the number of degrees of freedom. This is an underwater robot, which is actually belongs to a 6-thruster underwater robot. Belongs to, again, Carnegie Mellon. And we do have 2 underwater robots that I believe none of you probably are working with, Ben Champion. But nevertheless, he has done quite a bit of work on his PhD at Deakin University in Australia. And so underwater robot and air robot are much more difficult to model and to control compared to the land rovers, as you will see. Okay. And of course, this boat is underwater, not under the water. And it's an autonomous boat. Okay. And as you can see, it has GPS, it has other sensors. So we will have in the toolbox, we have means to model and actually control several different versions of mobile platforms, mobile robots, including the ones similar to in the lab, although all of the works in the course, I'm just noticing, are wheeled robots. In the lab, we have track robots. Those are even more difficult to model. Okay, but it would be a good master's thesis to get into the track robot. So now let's look at mobile robotics. Mobility has several different phases and formats. Consider a train. A train is on a pre-specified fixed rail moving either forward or backward. So it has only 1 degree of freedom. Okay? And one actuator, the motor which runs it, motor goes back and forth. Okay? If you look at a bicycle, which is what the model has done in the toolbox for you here, and we go into it very much detail. The bicycle has essentially 3 degrees of freedom, the X and Y location of the bicycle and the direction which is going to go. And it's front wheel drive, the one that you are paddling yourself, okay? And the back rear wheel is just following that. And you can approximate, first of all, let me just show you what we just said about mobile car-like mobile robots. Train has 1 degree of freedom, one actuator, and is so-called fully actuated. Hovercraft, I don't know, have anybody has been on a hovercraft? I have been a few times. It's like basically a bus on the water, okay? And it has 3 degrees of freedom, again the direction and the X and Y location on the surface of the water. It has 2 actuators, so it's under actuated, not fully actuated. A helicopter, as we said, has 6 degrees of freedom, X, Y, Z, and pitch, yaw, and roll, or theta X, theta Y, theta Z angles. It has 4 actuators, and it has a gravity to go with in addition to that. It's still under actuated. Fixed wing aircraft, similar to helicopter, 6 degrees of freedom, 4 plus G, under actuated. 6-thruster AUV, autonomous underwater vehicle, 6 degrees of freedom and 6 actuators. Because you need a lot of help under the water. And GPS and other things are not available, it's tough to control, so it's built that way. So it's fully actuated. And your car, you're driving it every day. You have 3 degrees of freedom. X and Y location of the gravity of the car and the direction you're driving. It has 2 actuators and it's under, okay, one actuator is going to actually depend on the input to that system. Your car is let's say a block diagram. The input to your car is your gas you put on your wheel, and the wheel, the steering wheel that you move. Those are the inputs to your car. And your output are 3 variables: X and Y location of the car and the direction it's heading. Okay. So now let's look at anatomy of a bicycle and approximate one for the car. You can see here that all the light gray parts are parts of your car, and the dark gray one is the bicycle. This could be the front wheel of the bicycle, this is the back side of the bicycle, and in general, in the car you have gearbox connecting these together, front and the back, and similarly for a bicycle, you are all connected together. The location of the center of the bicycle, let's say in this point, compared to the overall coordinate system O, X and Y are the 2 variables, and the orientation theta is the 3rd variable. However, when you are behind the bicycle and you are moving bicycle to the left or to the right, you are steering it through an angle called gamma. That's your steering angle. And here you see basically 2 circles. One circle goes through the center of the rear wheel, another circle goes through the center of the front wheel. R1 and R2 are the 2 radii of these 2 circles. If I draw a tangent to the first one and another tangent to the second one and put these dashed normals on those lines, they intersect at the point I say it's called ICR, instantaneous center of rotation. Okay? And because of the triangular condition of the two sides here are normal to those two lines, the value of gamma in here is identical to the value of gamma there. You can check it easily, basically, by looking at the triangle. Okay. Now, L is the wheelbase of that. Okay. So, the velocity of bicycle in the x and y direction are x dot and y dot with respect to v coordinate system. Remember when we talked about manipulated robot, we start from the base coordinate, you go to the shoulder, you go to the elbow, and so forth. Same thing here. You start from O, you go to V. A second coordinate system, which is shown in red. Okay, so with respect to V would be x dot, we call it V, and y dot equal to 0. Why y dot is equal to 0? Because the wheel cannot go sideways. Okay, it only can go x way.
Yeah.
Okay. Of course, I will show you maybe beginning of the next lecture. I'll show you our 3D printed robot that we built last year in this same course with a Swedish type of wheel which goes to the side, it goes to the front, it goes everywhere. Okay, and that is the exception to this rule. So the radius, the rate of change of theta in radian per second of any arc you can imagine is going to be the linear velocity divided by the radius. This comes from geometry, which you can go and check in the appendices, and from that we can solve for R1. R1 is going to be equal to V divided by theta dot, but if you look at right here, this triangle, this right here is equal to what? This is equal to L. And this is going to be, let's say, R1. So the tangent of gamma is equal to this divided by that, divided by this, sorry about that, is equal to this divided by this. So looking at the tangent relationship, you get R1 is L over tangent of gamma. Okay, that's how you come up with that equation. Now, one thing which is interesting to do is the following, that L is the length of the vehicle or base. As we would expect, the turning circle increases with vehicle length. The longer the vehicle length, the larger this circle is. Now maybe you recognize that the trucks which have such a long base, they have to take a very long, very large circle to be able to turn around. Okay? Next time they do, remember this concept. The larger the base, the larger this circle is going to be. Okay? This right here. This circle R2 right here. This circle. Okay. Now, let's see, if you look at velocity, vector, and if you project it on the x-axis and y-axis, the components of the velocity in x dot and v dot are going to be equal to v times cosine of theta, y dot equal to v times sine of theta. These are the projection values of the velocity vector on x and y coordinate system. Okay? Which is very similar to what you already know in vector analysis. You have a vector with a length r, on the x is r times cosine of theta and r times sine of theta, the two components. Okay? And then of course from this equation right here, or this equation, we have theta dot is v over L times tangent of gamma. Okay? So these three equations in equation 4.2 are all you need to know in mathematically model a mobile platform on the land. On the land. You know, later on you're going to be doing a homework on these subjects and later on an experiment in the lab on mobile robot. If you want to simulate a mobile robot, that's what you need right here. Now, the two inputs of the system are what? Gamma and V. Velocity, remember, putting your foot on the gas, you're increasing the velocity. And you're steering the wheel, you're changing gamma. Okay? So gamma and V are the input to your system. What are the outputs? X, Y, and theta. Okay? So this is a very simple but very meaningful equation. Now, notice that if the angle theta becomes 90 degrees, x dot is becoming 0, and y dot is equal to v, then it will be impossible for a robot to move like this because it can only go to the y direction, x direction. Okay. Furthermore, this equation is in a sense similar to forward kinematics of a manipulator. Remember what we said about kinematics is the study of mobility of relationship between chain of links of a manipulator, regardless of the forces and torques that created that movement. So this model is called a kinematic model since it describes velocity of the vehicle, but not the forces or torques that cause the velocity. Okay. The rate of change of theta dot is referred to as the turn rate, heading rate, or yaw rate, and can be measured by a gyroscope. It can also be deducted from the angular velocity of the wheels on the left and the right hand side of the vehicle, which follows arcs of different radius. If I divide this equation by this equation, y dot over x dot over y dot is going to be equal to cosine theta times divided by sine theta. The velocity will get cancelled out. This equation shows up. This equation is called a non-holonomic constraint. What is the non-holonomic constraint? A non-holonomic system is one whose state depends on the path taken in order to achieve it. I repeat, a non-holonomic system is one whose state depends on the path taken in order to achieve it. In other words, if you want to go you're driving your car, going from here to your home, it's a non-holonomic system, your car. You need to take that path toward your house to be able to get there. Okay? It's a simple idea, but they have given it a fancy name. Okay. As we said earlier, equation to capture some other important characteristic of the vehicle, when velocity is zero, if velocity v is zero, then theta dot is also zero. That is, it's not possible to change the vehicle orientation when it is not moving. Very obvious. When the car is moving, you're not going to go anywhere. You cannot change it. Okay? If it's run out of gas, of course you can put it on the neutral and you can push it. But that's about it. Okay? By itself, it cannot do that. Okay? So let's stop for the first session and we go after that.